Welcome back to the Deep Dives, where we unpack complex topics, distill fascinating insights from our sources, and aim to make you not just informed, but truly well-informed.
Glad to be back.
Today, we're embarking on a journey into something incredibly fundamental, something we all encounter from, well, our earliest days in school, but often don't fully, understand. We're talking about the foundational building blocks of numbers.
Right.
Specifically decimals, fractions, and even how we measure the world around us.
Yeah, the real basics.
But our mission isn't just about getting the right answer, is it? It's about peeling back the layers to truly grasp why that answer is correct.
Exactly.
And maybe what might be holding us back from that deeper understanding.
And this deep dive, it's guided by some truly illuminating educational analyses from around the world, actually.
Okay.
And it's going to reveal something profoundly important. We'll explore how certain teaching methods, often well-intentioned, maybe even seemingly helpful.
Ones we probably all experience.
Very likely. How they can inadvertently create what our sources call conceptual hurdles for learners. You might have even felt them yourself. We're going to show how a deeper, more unified understanding of the underlying mathematical principles can just make all the difference.
Right.
And demonstrate why some common difficulties in math are inherent to the learner, but maybe, just maybe, a product of how these concepts are introduced and discussed.
So it's about challenging some assumptions.
Absolutely. Giving you a new lens, really, to view mathematics.
So our quest today, then, is to systematically unpack these foundational concepts. We'll look at how the very language we use profoundly shapes our understanding.
Which is huge.
Sometimes for the better, sometimes, well, for the worse. And ultimately, we aim to offer you a more intuitive, more durable, and infinitely more transferable way to grasp what can often feel complex or abstract.
Yeah.
We've meticulously combed through a stack of research, primarily from the field of mathematics education, to guide us on this.
And we'll be focusing on a series of concepts that are really designed to build a truly robust mathematical foundation.
Okay.
Now, while this is especially crucial for students in, say, the 10 to 12 age range.
That middle school transition.
Exactly. The insights we'll share are genuinely beneficial for anyone, whether you're a parent, helping with homework, an adult maybe looking to solidify your own understanding.
Or just curious.
Or just intensely curious about, the architecture of numbers. We'll be looking at the fundamental anatomy of numbers.
Okay.
How to approach basic operations without just relying on tricks.
Right, the why behind them.
Yes. And even how to master something as common as unit conversions, all through this lens of conceptual clarity that goes way beyond just rote memorization.
Okay, so to truly build this robust foundation we're talking about, we need to go right back to the very atoms of numbers themselves.
We really do.
Our sources, and I know some draw heavily from influential French educational analyses, they highlight 4 absolutely crucial concepts. The bedrock of numerical understanding.
That's right.
What are these fundamental pillars, and how does understanding their individual roles unlock that deeper grasp, especially with decimals?
Indeed. For a profound and really lasting understanding of numeration, how numbers are structured, how we read them, mastering these 4 fundamental concepts is absolutely essential.
Okay.
And these aren't just, dry definitions. They are the base, the very foundational elements upon which all subsequent mathematical learning is built. If we miss these, well, we're building on shaky ground.
Makes sense.
Let's break them down, starting with the most basic. First, we have what our French sources call le chiffre.
Chiffre. Okay.
Or, as we would simply say in English, the digits.
Right, 0 through 9.
Exactly. Think of it as the single visual symbol itself, the drawing from 0 to 9. It's the raw material of numbers. So, for example, if we look at the number 537.4,
Okay.
the individual digits are just 5, 3, 7, and 4. It's just the character, nothing more.
Like a letter in the alphabet.
Precisely. By itself, it conveys little, but its placement changes everything.
Got it. What's next?
Next, every digit has a place, right? A home within a number. And that's what they refer to as le nom de la position,
Position name.
or simply the position name. This refers to the specific name of the column, or you could say the rank, where a particular digit sits.
Okay.
So, sticking with our example, 537.4, the digit 3 isn't just a 3, it's in the tens position.
Right.
And the digit 4 isn't just a 4, it's in the tenths position.
Okay, so like its address.
Exactly like the address. It
Digits
tells
like-
you the kind of neighborhood the digit lives in, gives it context within the number structure.
Right. 2 down.
Then there's La valeur de la position.
Value of the position.
The position value. Now, this is the actual quantitative worth that that column itself represents, regardless of the digit that happens to be sitting there.
Okay. The value of the address itself.
You got it. It's always 10 times larger than its neighbor to the right and 10 times smaller than its neighbor to the left. These are the values we kind of instinctively know. 1,000, 100, 10, 1.
And then pass a decimal.
It's moving past the decimal point. 0.1, 0.01, 0.01, 0.01, and so on.
Okay.
So for our tens position, its inherent value is 10. For the tenths position, its value is 0.1. This is the magnitude that the column itself stands for, the power it carries.
The value of the property on that street, like you said.
Exactly. And finally, and this is critical, we arrive at la valeur du chiffre.
The digit value.
The digit value. This is what the digit truly represents within the number. Its actual worth or quantity in that specific position.
Ah, the combination.
Yes. It's calculated as the digit multiplied by its position value.
Okay.
So in our number 537.4, the digit 3 has a value of 30. Why? Because it's the digit 3 multiplied by its position value of 10.
3 times 10. Got it.
And the digit 4 has a value of 4/10, or 0.4, because it's the digit 4 multiplied by its position value of 0.1.
4 times 0.1.
Precisely. This is its real contribution, its genuine power, to the overall quantity of the number. It's the total worth of your house, considering its size and its location.
So if I'm getting this right, digit value is really the sum total of that digit's power within the number. It takes this position into account. It's the what it actually means piece, isn't it?
That's the perfect way to put it, yes.
So this isn't just about like identifying the individual parts then. It's truly understanding their distinct and absolutely critical contributions to the whole number.
Exactly.
For instance, knowing these 4 concepts allows us to genuinely break down 537.4 not just as a string of symbols, but as the sum of its digit values. 500 plus 30 plus 7 plus 0.4.
The decomposed view.
Or, even more fundamentally, as 5 times 100 plus 3 times 10 plus 7 times 1 plus 4 times 0.1. This detailed, almost architectural understanding. It isn't just academic, is it? It's absolutely key for building that strong, flexible, resilient foundation that prevents so many common errors later on.
It's completely foundational. It makes the abstract concrete.
Understanding the individual contributions of each digit in a number is clearly foundational. But it seems some of the most persistent difficulties we run into, particularly with decimal numbers, pop up precisely when we lose sight of that unified structure.
That's a really critical point.
What exactly happens? How do we unwittingly create what's been termed the decimal point barrier?
You've hit on something crucial, the idea that decimals are inherently challenging. Well, our research suggests it's often more of a pedagogical bias.
A bias in the teaching.
Yes, a bias rooted in how we typically teach these concepts, rather than an innate difficulty for the student. A very common teaching method for comparing decimals involves a 2-step process.
No way.
First, you compare the whole number parts. Fine. But if those are equal, and this is where the issue really arises, you then compare the decimal parts as if they were completely separate integers.
Oh, I think I remember this. Like comparing 4.2 and 4.1D.
Exactly that example. A student's often told, compare the 4s. Okay, they're equal. Now compare the 2 with the 18.
Right, and 18 is bigger than 2, so.
Oh, bingo.
Here's where it gets really interesting and, frankly, a bit insidious, like you said. This 2-step comparison method is, as our sources strongly highlight, a pedagogical trap.
It truly is.
It inadvertently encourages students to mentally, kind of, partition a number like 4.18, not as a single quantity,
No.
but rather as 2 distinct integers, 4 and 18, that are just separated by that little dot.
Yeah, they create what our French sources call a virgule frontière, a decimal point frontier. It's like this artificial wall that breaks the number's integrity and completely confuses its true value.
Like saying house number 12.5 is 2 separate numbers, 12 and 5, just stuck together.
It's exactly that kind of flawed thinking. And this mental partitioning leads directly to classic, very common errors like that pervasive longer is larger bias.
With a number with more decimal digits seems bigger.
Precisely. Imagine a student comparing 4.2 and 4.18 again, using that flawed separate integers logic. First, the whole parts are equal both 4.
I think compare 2 and 18.
Right. They proceed to compare 2 with 18. Because 18 is clearly larger than 2, they incorrectly conclude that 4.18 is greater than 4.2.
Wow.
Now, this isn't a failure of the student's reasoning. In fact, it's a successful application of a flawed, pedagogically induced logic.
They did what they were told.
Exactly. They were doing exactly what they were implicitly taught to do. The problem isn't the child, it's the method.
That longer is larger bias is so pervasive. I've seen it myself. But for educators or even parents listening who might have been taught with that two-step method themselves, I mean, what's the biggest barrier to adopting a new, more unified comparison? Is it a hard habit to break?
It absolutely can be a difficult habit to break because, honestly, it feels efficient in the moment.
Yeah, it seems quick.
The biggest barrier is often that perceived simplicity of the old way, maybe mixed with the time crunch teachers often face.
Yeah.
But the long-term cost and conceptual understanding is just immense. To overcome this, we absolutely need a unified method. One way to compare all numbers, with or without decimal points, that completely avoids this barrier.
Okay. And this method relies on comparing the digit value. Those fundamental concepts we just nailed down, from left to right, stopping immediately at the first point where a difference is found.
Treating it as one continuous quantity.
Exactly, not two separate pieces.
Yeah.
Let's walk through that specific example again, comparing 4.2 and 4.18 using this unified approach.
Okay, step by step.
Step 1, we start from the leftmost digit. That's 4 point in both numbers.
In the units position.
Right, in the units position. So its digit value is 4 units. They are equal. So we continue, moving right.
Okay.
Step 2, we move to the next digit. This is in the tenths position. In 4.2, the digit is 2. Its digit value is 0.22 tenths.
Got it.
In 4.18, the digit in the tenths position is 1. Its digit value is 0.11 tenth. Notice we're not comparing 2 to 18.
No, you're comparing 0.2 to 0.1.
We're comparing the value of the digit in that specific position.
Okay.
Yep. Step 3, now we compare these digit values. 0.2 versus 0.1.
And 0.2 is clearly bigger.
Clearly greater, yes.
Step 4. This is where we stop. Because we've found a definitive difference right there at the 10th place, anything that comes after this point, it doesn't change the comparison.
The 8 doesn't matter anymore.
Exactly. We don't need to even consider the 8 in 4.18 because the relationship has already been established. The first point of difference decides it.
So the conclusion is 4.2 is greater than 4.18.
Our conclusion, therefore, is that 4.2, 4.18. This approach fundamentally treats the number as a whole. It prevents that natural number bias from taking root because it doesn't artificially split the number at the decimal point.
Right.
It builds directly on understanding each digit's true value, that concept we laid out right at the start, making the understanding durable and, importantly, transferable.
Okay, so once we understand the fundamental structure of numbers, each digit's true value, how does that conceptual clarity change the way we think about basic operations? Addition, subtraction, and especially I'm thinking multiplication.
Yeah.
It feels like we're laying down foundational rules that should just extend naturally to everything else.
You're absolutely right to connect it. The challenges definitely don't stop at comparison. They extend deeply into operations.
Okay.
Think about traditional methods for addition and subtraction. We learn align numbers to the right for integers. Then, for decimals, there's this seemingly separate rule, align the decimal points.
Yeah, two different rules.
Right. They're often presented as tricks or just procedural rules rather than mathematically logical methods. And this often leads to significant confusion, particularly when, say, one number is an integer and the other is a decimal, like trying to add 23.7 plus 97.
Where do you put the 97? Under the 23 or the 0.7?
Exactly. Students struggle with how to apply these seemingly different rules, and they often misalign values because the underlying logic isn't clear.
I remember a moment in my own learning, maybe 3rd or 4th grade, where I made exactly that kind of mistake. It was like I had 2 different rule books, and I tried to superimpose the 4 and 5 in an operation like, say, 1.4 plus 0.15.
Oh, classic error.
And you'd get something like 1.59. Right? Because you're basically adding tenths to hundredths as if they're the same kind of thing, which is just fundamentally wrong.
It's a textbook symptom of not understanding the underlying positional structure.
Exactly.
So how does this same nature principle help here?
Well, that rule, align the decimal points, is fundamentally just a procedural crutch.
It works, but you don't know why.
Precisely. While it does lead to the correct answer, it rarely explains why it works. And as you pointed out, For many students who perceive the decimal point as that frontier,
Yeah.
this rule can even reinforce the idea that there are two separate calculations happening, one on each side of this imaginary boundary. It doesn't build a cohesive, unified understanding.
Right.
The conceptual approach, though, changes this entirely. The guiding principle becomes you can only add or subtract quantities of the same nature.
Ah, okay. Apples and oranges. Exactly. It's a fundamental algebraic thought, really. A principle that underpins so much of higher mathematics. You can't add 3x and 2y without some kind of conversion, because they're quantities of different nature.
So it's not about the dot.
No. So instead of aligning the decimal point, you align digits that represent the same position name.
Okay.
So, for example, to accurately pose the operation 12.4 plus 385, an understanding of position value means you would. First, identify the unit's place in both numbers.
The 2 and the 5.
Right. The 2 from 12.4 is units, the 5 from 385 is units. So you align them vertically.
Okay.
Second, identify the tens place. The 1 from 12.4 is tens, the 8 from 385 is tens. Align them.
Got it.
And as you do this, you'll see that empty places are perfectly fine. There's no need to be surprised or to, add extra zeros as a trick initially.
Right.
The decimal point then naturally aligns itself because it consistently separates the unit's position from the tenths position. For 385, it's implicitly 385.0, right? This approach builds a deep mathematical structure, crucial for later algebraic concepts. It teaches students to think about the value of what they're combining, not just symbols on a page.
One of the biggest myths I think many of us carry from our early math classes is that multiplication always makes things bigger.
Ah, yes.
It's deeply ingrained. Times means more, right?
Yeah.
But then you start thinking about decimals or fractions, and that idea just completely falls apart, doesn't it?
Completely collapses, yes.
Why is this misconception so persistent? And how can we overcome it?
You've perfectly articulated what our sources call an erroneous conception. This deeply held belief that multiplication always results in a larger product.
Yeah.
It's perfectly valid, perfectly intuitive for whole numbers greater than 1. Think 3 by 5 equals 15. Bigger.
Sure.
But this intuition completely collapses when we start working with fractions or decimals less than 1. For instance, if you multiply 4 by 0.7,
You get 2.8.
the product is 2.8, which is undeniably smaller than 4. This is a classic example of what's known as natural number bias, or BNM. Okay.
Where students inappropriately apply properties that are true for whole numbers to rational numbers. It leads to these deep-seated errors and a lot of confusion.
It's like using a hammer for every jog.
Exactly. Even when you need a screwdriver.
And a big part of that bias probably comes from how we first learn multiplication, right? Those traditional explanations often point to the repeated addition model.
Yeah.
5 plus 5 plus 5.
Like 3 by 5, meaning 5 plus 5 plus 5. That works brilliantly for whole numbers. But how do you add 5 0.3 times?
You can't.
It doesn't make any intuitive sense.
But sure.
The model breaks down completely, leaving learners kind of stranded without a conceptual anchor.
You've hit on the critical point. This is precisely where the linguistic hypothesis becomes so crucial, as demonstrated by extensive research.
Language again.
Yes. The oral phrasing of multiplication fundamentally influences understanding. If we, as learners or teachers, read an expression like 0.3 by 5 as 0.3 times 5, which sounds natural. It sounds natural, but it very strongly evokes that repeated addition model you just mentioned. And as you said, that model breaks down immediately. It creates profound conceptual confusion because you just can't logically add 5 0.3 times. The language we choose creates this barrier. However, if we shift our oral phrasing, if we read it as 3/10 of 5...
Of 5, okay.
It implies a completely different operation. It naturally suggests a taking a part of or a scaling down operation.
Right, like a fraction of something.
Exactly. This linguistic framing leads intuitively to a smaller result, 1.5 in our example. And the beauty of this is that the oral expression now aligns directly with the actual mathematical effect of multiplying by a number less than 1.
The language provides a bridge.
A vital conceptual bridge, yes. It makes the operation's outcome logical rather than counterintuitive.
So the word times carries this sort of baggage of repeated addition, which is only true sometimes.
Right.
While the word of aligns much more cleanly with the idea of scaling or taking a portion. This is subtle, isn't it? But incredibly powerful in how we frame the operation, like a hidden curriculum in our everyday language.
It really is.
What kind of cognitive shift does this require for someone who's been thinking times means bigger for well, years.
It requires a significant cognitive shift, a genuine rewiring of intuition, you could say.
Yeah.
It's about expanding the very definition of multiplication in our minds.
Absolutely. The language we use isn't just a transparent communication tool. Our sources show it actively shapes mathematical thought and understanding.
Right.
To overcome this deeply ingrained multiplication makes bigger bias, we need to shift from seeing multiplication only as repeated addition to also understanding it as scaling or taking a fraction of a quantity.
Broadening the definition.
Exactly. This prepares students for a much broader range of mathematical applications like calculating areas, adjusting recipe proportions, understanding financial growth rates, determining percentages.
Where scaling is key. Where scaling is an inherent part of the concept, yes. It's about building a more resilient mathematical intuition.
Can you give an example?
Absolutely. Let me give you an illustrative example from the source, using fractions as operators. This really demonstrates the reduction of natural numbers and makes the scaling idea very concrete. It explicitly challenges the multiplication makes bigger bias. Consider these.
Okay.
When we see 10, 12, if we read it as 1/2 of 10,
The answer is 5.
the result is 5. This clearly shows that 5 is half of 10. The number 10 became smaller when multiplied because we took a part of it.
Right. Makes sense.
Similarly, 12, 13 read as 1/3 of 12 is 4, results in 4. Here, 4 is 1/3 of 12. Again, the number became smaller.
Okay.
And even simply, consider 113 if we read this as 1/3 of 1.
The result is 1/3.
The result is 13. This explicitly shows that 13 is 3 times smaller than 1. It's not just a numerical result, it's a conceptual statement about how multiplication works with fractions.
That's incredibly clear. This table explicitly shows multiplication by a proper fraction resulting in a smaller number. It forces you to rethink the operation away from just repeated addition.
Exactly.
It directly attacks that multiplication makes bigger bias we talked about, using fractions as the tool.
Absolutely. It's about building a consistent, unified understanding across different types of numbers.
Speaking of fractions, the pizza slice model is everywhere.
Oh, yes. Ubiquitous.
It's probably how most of us were introduced to fractions, visually, tangibly. But what are its limitations? And how could we rethink fractions to give learners a stronger, more flexible foundation that goes beyond just parts of a whole?
The pizza model, or more broadly, the whole part approach, it is visually intuitive for a very initial introduction. Simple fractions like 12, 14, great for understanding sharing.
Sure.
However, while it's good for that initial introduction, our sources really highlight that it fosters a very limited understanding. It frames fractions primarily as mere parts of a whole,
Not as numbers themselves.
rather than as numbers with their own distinct magnitude and position in the number system.
Yes. And this limited view often leads directly back to that same whole number bias we discussed with decimals.
How so?
Well, students, applying that whole number logic, might incorrectly assume that 18 is greater than 14.
Because 8 is larger than 4.
Precisely. Just as they would compare two whole numbers. The larger denominator, to them, means a larger number, which is exactly the opposite of reality for fractions. The pizza slices get smaller as the denominator gets bigger.
And that pizza slice limitation makes it really tough to visualize fractions greater than 1, like 74.
Oh, definitely.
You'd need multiple pizzas just to show it. It becomes cumbersome, less intuitive than it should be.
Right.
And it also makes it difficult to intuitively grasp operations like multiplying fractions, where the result can often be smaller than the factors. If your only model is parts of a whole, how do you logically combine parts to get something even smaller?
It breaks down completely. You're right.
So what's the fix? To truly overcome these limitations, we need to introduce fractions primarily as numbers,
Okay.
each with a unique magnitude and a specific, well-defined position on a number line.
The number line. Okay.
Number lines are incredibly powerful visual aids here because they depict fractions not just as slices, but as destinations on a continuous journey.
Points on a line.
Yes. Imagine trying to explain 74 with pizzas, like you said. You'd need 2 whole pizzas and then 3/4 of another. It's awkward.
Yeah.
But on a number line, 74 is simply a point beyond 1 and before 2. It shows its magnitude as clearly as 1 3/4. It's just there.
A location.
Exactly. This dynamic perspective isn't just a mental trick, it's a foundational bridge. It helps us see fractions as real, usable numbers, just like integers, rather than just abstract components of something else.
Moving beyond the static part of an object view.
To a dynamic number with a specific value and effect perspective, yes.
How do we foster that?
We can introduce two key concepts to achieve this deeper understanding. The first is reduction of a natural number. This reframes division not just as sharing, but fundamentally as scaling down. When we ask, what is the number 3 times smaller than 1, we're implicitly asking for 1 divided by 3, which is 13.
Right.
Fractions, in this context, become operators that reduce a number. Think of multiplying 10 by 12 again.
Gives us 5.
Gives us 5. This explicitly challenges the multiplication makes bigger bias by showing a reduction. Here's a quick table to illustrate this powerful concept.
Okay.
For a natural number, say 10, when it's multiplied by the fractional operator 12, the result is 5.
Right.
We describe this relationship as 5 is half of 10. The fraction 12 acted as a scalar, reducing 10 to 5.
Got it.
Next, for the natural number 12, when multiplied by 13, the result is 4. Here we understand that 4 is 1/3 of 12.
Okay.
And crucially, consider the natural number 1. When multiplied by 13, the result is 13. This helps us visualize and articulate that 13 is 3 times smaller than 1.
Right.
It's not just a numerical equivalence, it's a conceptual statement about the scaling effect of multiplication by a proper fraction.
That's incredibly clear. And again, it explicitly shows multiplication by a proper fraction resulting in a smaller number, forcing that reconceptualization away from just repeated addition.
Exactly. It directly attacks the bias.
What was the second concept?
Absolutely. It's about building that consistent, unified understanding. Our second concept is inverse multiplicative comparison.
Okay, inverse multiplicative comparison.
This directly addresses the larger denominator, smaller fraction misconception that stems from that whole number bias.
The 18 versus 14 issue.
Precisely. It emphasizes that a larger denominator, the bottom number, signifying how many equal parts the whole is divided into, means the unit fraction, its reciprocal, becomes proportionally smaller.
Right. More pieces, smaller pieces.
Exactly. So 18 is conceptually understood as 8 times smaller than 1 because the whole is divided into 8 pieces, while 14 is 4 times smaller than 1 because the whole is divided into only 4 pieces. This clearly demonstrates, conceptually, why 18 is less than 14.
Makes intuitive sense that way.
And again, number lines are invaluable here. They help visually demonstrate that as the denominator increases, the unit fraction gets cut into smaller and smaller pieces, moving progressively closer to 0. Let's look at a quick table for this.
Okay.
If the denominator, let's call it n, is 2, then the unit fraction, 1n, is 12. We describe this as 12 is 2 times smaller than 1. And the inverse multiplicative relationship is simply 2, meaning 1 divided by 5 equals 2.
Got it.
If the denominator n is 3, the unit fraction 1 is 13. Here, 13 is 3 times smaller than 1, and its inverse multiplicative is 3.
Okay.
For a denominator of 4, the unit fraction is 14. 14 is 4 times smaller than 1, and its inverse multiplicative is 4.
I see the pattern.
This table powerfully highlights the inverse relationship between the size of the denominator and the magnitude of the fraction. It helps learners move beyond just rote memorization of comparison rules like cross-multiplication to a deep, intuitive, conceptual understanding of why a larger denominator yields a smaller fraction.
So what does this all mean for us, for the listener? We're moving from a static part of an object view, that pie chart mentality, to a dynamic number with a specific value and effect perspective. This isn't just about understanding fractions better in isolation, is it?
Not at all.
It's about preparing students for abstract manipulation in algebra, where quantities are constantly scaled and transformed, and we're understanding the inherent magnitude of a number, regardless of its form, fraction, decimal, whatever, is absolutely critical.
It's absolutely crucial for future success.
We've seen how rethinking numbers themselves and their operations can resolve so many issues. But there's another common challenge where our traditional methods often fall short. Unit conversions.
Ah, yes. The bane of many students' existence.
It's an area where many of us, myself included, just memorize charts. But our sources suggest that, again, a deeply conceptual approach changes everything.
Let's pivot now to the grand challenge of unit conversions. Unit conversions. Things like converting meters to centimeters or grams to kilograms. They indeed represent a persistent and frankly significant challenge for a large percentage of students.
Really?
Still.
Oh, yes. Evaluations have consistently shown that even basic conversions like 400 meters to kilometers are only correctly answered by about half of students entering middle school.
Wow, only half.
And this isn't just about, calculation errors. It's a telltale sign of a lack of deep conceptual understanding of magnitude, of measurement, and critically,
how different units relate to each other in a proportional way.
It's lacking that internal sense check.
Exactly, that sense of whether an answer is even reasonable.
I certainly remember using conversion tables in school. You know, the columns. Meters, decimeters, centimeter.
Well, the grid?
You write a number in a specific column, then fill in empty places with zeros, or maybe move a decimal point. It seems simple enough. A very practical trick to get the right answer quickly. It worked, mostly.
And that's precisely the conversion table paradigm. It's a procedural visual algorithm.
Yeah. You place the unit digit of your starting number in the column that corresponds to its starting unit. Then you fill in empty places with zeros until you reach the target unit's column, and then you read the result, adjusting the decimal point as needed.
Right.
For instance, to convert 67.8 grams to milligrams, you'd typically place the unit digit of the grams value in the grams column. The 6 goes left to deg, the 8 goes right to dg.
Okay.
Then you'd add zeros all the way across to the milligrams mg column,
Filling the gaps.
effectively getting 67, 800, 800 milligrams. It offers an apparent efficiency and security, a clear recipe to follow.
Seems easy.
But this apparent simplicity comes at a significant cost, a really significant cost.
Okay, but you're saying this approach, despite its apparent simplicity and, let's face it, wide use, has fundamental hidden dangers. Things that undermine true mathematical understanding.
Yes, it has fundamental and significant risks. They build what our sources refer to as didactic obstacles created by the teaching method itself.
Okay, what is it?
First, there's a profound loss of meaning. It becomes an automatic but blind process.
Just following steps.
Exactly.
Well.
Students aren't consciously multiplying or dividing by powers of 10. They are simply following a visual rule on a grid. This leads to what we call know-how without knowing why.
Right.
They can mechanically do the conversion, but they don't understand the underlying mathematical relationship between the units. It's like being able to drive a car by following a diagram of which pedal to push, but having no idea how the engine actually works.
And if something goes wrong,
If anything deviates, they're completely lost. Second, this leads directly to fragile learning.
meaning it doesn't stick.
Exactly. Such purely procedural knowledge, disconnected from concept, is easily forgotten, especially under pressure. Students frequently forget the rules, make errors in placing numbers on the table,
Yeah.
and critically are completely unable to check the plausibility of their answer because they lack the underlying reasoning.
The sense check again.
Yes. Picture a student, diligent but disconnected. They've used the table for years, meticulously sliding numbers, adding zeros, but then under pressure, they misplace a digit, forget a rule. An error like converting 400 meters to 0.004 kilometers.
Which is way too small.
Right. It might not even register as absurd to them because they haven't built that concrete mental image of a kilometer being so much larger than a meter. It's like having a perfectly drawn map but no idea of the scale.
Makes every journey feel the same.
Right. This lack of intrinsic reasoning means they can't sense check their answers, and that's incredibly limiting.
Okay, what else?
Third, and this is crucial, it fosters a decimal point misconception.
How so?
The table, visually, often encourages the erroneous idea of a moving decimal point.
Yeah, the hopping decimal.
Exactly. This is a major didactic error. It undermines the very foundation of our number system. The decimal point is a fixed separator defining the unit's position. It's the digits that shift their value when multiplied or divided by powers of 10, not the point itself.
Right, the values change, not the separator.
Precisely. This method actively deconstructs a proper understanding of the decimal number system, which is a far more fundamental concept than unit conversion itself. It reinforces a falsehood about how numbers actually work.
Wow, that's a big one.
It is. And finally, it results in profound inflexibility. The conversion table is a rigid, single-purpose tool.
Only works for metric.
Its structure is entirely tied to the metric decimal system. It's completely useless for non-decimal conversions like time hours to minutes or angles, or for converting rates like kilometers per hour to meters per second.
Right, you can't put hours and minutes in those columns.
Exactly. Those require more complex proportional reasoning. The table gives students a crutch for a very narrow range of problems, rather than a versatile intellectual tool that works across all measurement systems. It fails to build transferable knowledge.
So if the conversion table is truly a didactic obstacle, creating these fragile, superficial understandings, what's the alternative? What builds deeper understanding and a more robust mathematical tool set?
The alternative is what we call the return to unit method.
Return to unit. Okay.
This approaches conversion not as a trick or a table lookup, but as a problem of proportionality, which is a core mathematical concept.
Right.
It explicitly models the relationship between two units as a perfect proportional situation. For example, the length in centimeters is always 100 times the length in meters. LC meter equals 100 times LM.
Okay.
This method is structured in two logical, mathematically sound steps that actually build meaning.
All right. What are they?
Step 1. Find the value of the starting unit by division. You explicitly state the fundamental relationship between the two units. For example, 100 centimeters equal 1 meter.
Okay, the basic fact.
Then you reason. If 100 centimeters equal 1 meter, then 1 centimeter must be 100 times less than 1 meter.
Makes sense.
So to find the value of 1 centimeter in meters, I divide 1 meter by 100.
1 divided by 100.
This means 1 centimeter equals 1,100 meters, which is 0.01 meters.
Yeah.
You're essentially performing a division to find the value of a single unit of your starting measurement in terms of your target measurement.
Okay, find the value of 1. What's step 2?
Step 2. Calculate the target value by multiplication. Once you know the value of 1 unit of your starting measurement, you can easily calculate the value of the quantity you actually want to convert.
Okay.
Following our example, if 1 centimeter is 0.01 meter, then 35 centimeters is simply 35 times more than 1 centimeter.
Right.
So you calculate 35 centimeter is 35 multiplied by 0.01 meters, which gives you 0.35 meters. You multiply the value of 1 unit by the quantity you started with to scale it up.
That's fascinating. It's exactly like solving a really familiar proportional problem, isn't it? Like, if 3 bags of coffee cost $2.40, how much do 5 bags cost?
Exactly.
You first find the cost of 1 bag,
I divide in?
then multiply by 5. It's the exact same proportional reasoning just applied to units of measure.
Yeah.
That universality must be incredibly powerful.
Exactly. That's the beauty of it. This method doesn't just give you an answer, it builds deep meaning.
Yeah.
It reinforces fundamental multiplicative logic, and it powerfully unifies mathematical knowledge by connecting measures to the broader universal concept of proportionality. And, as you implied, it's also incredibly flexible and transferable. It works for time, hours to minutes, money, dollars to cents, rates, kilomilers to ems, any proportional relationship. It equips students with a true intellectual tool, not just a limited, brittle procedure.
This raises an important linguistic question, though. We've been using the word unit quite a lot.
Mm-hmm.
But it seems to be used in 2 very different ways in mathematics, which must be incredibly confusing for learners, particularly when they're trying to grasp conversions.
You've identified a major linguistic and conceptual obstacle. Our sources call it the polysemy of unit, essentially, the multiple meanings of the word unit.
Polysemy, okay.
It's like a single word wearing 2 completely different hats in mathematics, which can be incredibly confusing if not explicitly clarified. There are 2 primary uses, and they are distinct.
What are they?
First, there's the unit of numeration. In numbers, unit refers to the value of the first digit to the left of the decimal point, what we commonly call the ones place.
Okay, the ones column.
Right. For example, in the number 345, the 5 represents 5 units of numeration. It's an abstract concept that defines the fundamental structure of the number itself, the elementary building block for counting and quantifying. It defines the 1 in the ones place.
Got it. Abstract structure. What's the other meaning?
Second, there's the unit of measure. In measurement, unit is a concrete reference standard that we use to quantify something physical.
Like a meter or a gram.
Exactly. For instance, in 7 centimeters, the centimeter is the unit of measure. It's a specific length, weight, or quantity chosen as a reference to quantify other similar magnitudes. It's directly connected to the physical world and the act of measuring. Think of a meter stick or a kilogram weight.
Okay, abstract versus concrete standard. And the conversion table, with its columns labeled for each unit of measure. That must make this confusion between the 2 meanings of unit even worse, I imagine.
Oh, absolutely. Tragically so.
It visually merges them.
Yes. The conversion table's visual structure tragically mimics the numeration table, ones, tens, hundreds. This leads students to incorrectly fuse the unit of measure, which is the column label, like M for meter or cm for centimeter, with the unit of numeration, which is the rightmost position in a whole number, the ones place.
Right.
So when a student places 427 centimeters into the conversion table, they're often taught to see it as 4 meters, 2 decimeters, 7 centimeters.
Breaking it apart by column.
Right. This reinforces the erroneous idea of a number being made of different pieces of units. They aren't seeing 427 of one thing centimeters. They're seeing it fractured into different unit types based on the table columns. This fundamentally entrenches the confusion about the polysemy of unit.
But their return to unit method by treating the number and the unit separately. That would clarify this distinction, wouldn't it? It forces that conceptual separation.
Fundamentally, yes, it does. In converting 427 centimeters to meters using the return to unit method, the reasoning is explicitly clear. We know 100 centimeter equals 1 meter, so therefore 1 centimeters equals 0.01 meters.
Step 1.
Then, if 1 centimeter is 0.01 meters, then 427 centimeters must be 427 times that value. So 427 centimeters multiplied by 0.01 meters, which equals 4.27 meters.
Okay.
In this process, the number 427 and the unit symbol, are treated as distinct entities that are manipulated mathematically. The number's unit digit, the 7, plays no special confusing role in the conversion process itself.
It's just part of the number 427.
Exactly. This method forces a clear distinction between the number as a quantity and the unit as a reference, thereby resolving the polysemy and building a truly robust understanding.
It sounds like throughout this entire deep dive, whether we're talking about the anatomy of numbers, decimals, fractions, or even unit conversions, the precise use of language is a recurring and absolutely vital theme.
It really is.
It's almost like a foundational layer beneath all these mathematical concepts influencing everything.
What's genuinely fascinating here is exactly that point. Language isn't just a transparent vehicle for ideas. It actively shapes our mathematical understanding. Decades of research, including compelling cross-linguistic studies, show that differences in how we name numbers or describe operations can significantly impact conceptual understanding. It can even explain disparities in mathematical performance.
Like how some languages name numbers.
Exactly. For instance, the systematic base 10 aligned way numbers are named in many East Asian languages like 10-1, 10-2 for 11, 12 can inherently reinforce base 10 understanding much more effectively than the less consistent English number names like 11, 12.
Oh, interesting.
This is not a small factor. It's a powerful hidden curriculum embedded within language itself.
So saying 3.08 instead of, say, 308
Yeah.
that can actually hinder a child's understanding of that number's true value, not just how they say it.
Absolutely. It reinforces the exact decimal point barrier we talked about earlier.
Right.
Informal, everyday language, even if technically correct in social use, can create this powerful hidden curriculum that subtly undermines formal instruction. 3.08 reinforces the idea of two juxtaposed integers 3 and 08 separated by a symbol. It feeds directly into that decimal point barrier.
Okay.
In stark contrast, saying 3 units and 800ths, or even more powerfully, 300 800ths, that actively builds a deeper understanding of positional value. It facilitates mental manipulation by explicitly stating the fractional part. It communicates the true magnitude.
It's not just being pedantic then.
Not at all. It's about building a fundamentally more accurate mental model of numbers.
And this applies to how we frame operations too, like that critical distinction between times versus of in the multiplication we discussed.
Precisely.
It's about choosing words that reflect the mathematical reality, not just the colloquial usage. This shift, then, it isn't just about correcting errors. It's about deconstructing and reconstructing meaning itself. Using language as a powerful, almost foundational tool to build a more accurate and intuitive mental model of how numbers work.
Precisely. This shift from informal, potentially misleading language to precise, mathematically grounded terminology is a crucial conceptual bridge.
Okay.
It allows students to make sense of what I'm looking at by translating abstract mathematical ideas into comprehensible linguistic expressions that directly align with the mathematical reality.
Right.
Teachers' linguistic practices serve as powerful models, and actively encouraging students to verbalize their reasoning using precise mathematical language. Well, it fosters a much deeper, more robust conceptual understanding.
And language illuminates the math.
It literally helps to illuminate the mathematics itself. It makes the abstract less daunting, more accessible. It's about providing clear mental handles for complex ideas.
Wow. This deep dive has truly challenged some of the assumptions I think maybe many of us carried about learning math. We've seen how seemingly simple teaching methods can, ironically, create these persistent conceptual hurdles, and how deeply interconnected all these seemingly disparate topics really are. The anatomy of numbers, decimals, fractions, conversion.
It's all part of one grand, coherent system.
Yes.
It really is.
And if we connect this to the bigger picture, it highlights a profound need for a fundamental shift in pedagogical approach, really across all levels of education.
Moving beyond tricks.
Moving away from rote memorization and procedural tricks towards methods grounded in deep conceptual understanding, where every step has a logical why that builds a more robust, durable, and transferable mathematical knowledge.
Yeah.
And this is especially vital for children in primary and middle school in that 10 to 12 age range we discussed, as it lays their future foundation. But honestly, the principles apply to anyone at any age wanting a deeper, more satisfying understanding of the numerical world.
So what does this all mean for you, the listener? I think it means that if you've ever struggled with math, perhaps feeling like you just weren't a math person, which so many people feel.
So many people feel that. It wasn't necessarily a personal failing. Sometimes it was a product of how concepts were introduced, inadvertently creating biases and barriers.
Right.
By understanding the true anatomy of numbers, by rethinking our operations through linguistic precision, by consciously choosing more accurate language, we can foster a much stronger, more intuitive, and ultimately maybe a more enjoyable grasp of mathematics for ourselves and for those we might be guiding.
And this raises, I think, an important final question for all of us to ponder. How much more could be unlocked in mathematics across all levels of education if we consistently prioritize deep conceptual understanding and precise language right from the very beginning? Imagine the profound impact if we actively avoided inadvertently creating those conceptual hurdles and biases that learners then have to struggle to unlearn later on.
It's not just about test scores.
No. It's not just about improving test scores, it's about empowering students with a foundational way of thinking that is absolutely essential for advanced mathematics, for algebra, and frankly, for critical, informed thinking in everyday life.
Thank you for joining us on this deep dive. Keep questioning, keep exploring, and most importantly, keep understanding the why behind the what.